Alright, so here's the deal. I could be playing video games, want to be playing video games, but I decided to take pity on you guys and I'm going to do an awkward screencast of myself working these problems and explaining what I'm doing so that if you have nothing better to do, you can watch it and maybe it'll help you more than just seeing the answers on the key. The ones that just require written responses, I'm going to go through a really brief response of. I've posted Miss Morrison's key on eClass already, and she gives much longer responses to all of those. So if you're just looking for the answers, or if you're looking for a super in-depth answer to the written ones, you should just go check out the key. If you want to see the process behind actually working one of the problems or just listen to me be awkward, then you are in the right place. All right, so the very first, for the record, the reason these are numbered so weird, 8B, 8D, 9A, these are literally the standards that we've been told will be covered. Okay, 8b says compare and contrast scalar and vector quantities, give an example of each. So, scalar just is anything that just has magnitude, which is amount, and then a vector has magnitude. I can write faster than I can talk, and I can talk faster than I can write, and it's weird. A vector has magnitude and direction. An example of a scalar is speed, where you only care about the numerical value of how fast they're going. And a vector example is velocity, where you care about how fast they're going and what direction they're going in. It's impossible to have a negative speed, but it's possible to have a negative velocity because it just refers to direction. All right, now 8D says use mathematical methods for vector addition to solve problems for vectors that are on the same line and perpendicular to each other. When they say on the same line, they mean that they're either going the same direction or in opposite directions, and then perpendicular obviously means when the vectors are at right angles. So this first one, a hiker travels 42 kilometers north. After a period of rest, the hiker returns back along the pathway 23 kilometers south. What is the hiker's resultant displacement? So the vector diagram here, we have 42 km north, then 23 km south. The resultant is going to be basically the piece that's left over right there. It's going to be 42 minus 23, which gives us 19 kilometers north. If they had both been north, then we would have added the two numbers, but because they're going in opposite directions, we subtract. Those should be easy peasy. This next one is more difficult. It says, what is the resultant displacement of walking 20 meters south, then 35 meters east, then 30 meters south again? The first thing you need to notice is that these two are in the same direction, so before we go any further, we should just add those two together. 20 meters plus 30 meters equals 50 meters. So now we have 50 meters south and 35 meters east. Drawn out, that would look like this. 50, 35. And then when vectors are at right angles to each other, your answer has three parts. Up here, your answer has two parts. It has a number, magnitude, and direction. But when you're dealing with when they're at right angles like this, then you have to worry about a third thing. You need magnitude, angle, and direction. So, the first one's the easiest, the magnitude. We're going to make this a triangle. We're going to say that's A, that's B, and this is C. We know that a squared plus b squared equals c squared. 50 squared plus 35 squared equals a really large number. I don't have my calculator. I know that the final answer, I'm sorry guys, the final answer when you take the square root of this is 61 meters. So you have C equals 61 meters. Then to find the angle, you use inverse tangent. So you do inverse the angle, which for the record is that angle. The angle equals the inverse tangent of b over a. In our case, that's inverse tangent of 35 over 50, which gives us 35 degrees. I will remind you the day of the test, but your calculator must be in degrees for physics things. And then finally, the third piece, the direction, you do short of long. That's direction. So the short of long here, 35 is shorter, so it's east of south. I kind of didn't leave myself any room here, but the entire answer written out would be 61 meters, 35 degrees east of south. I'll try to make sure I have room to write that out on the next one. So this one is just basically the same thing, except you don't even have to do this step at the beginning where you combine two. It says a plane is traveling at 385 kilometers an hour while the wind blows at 27 kilometers per hour. What is the plane's resultant velocity? So, north at 385, west at 27. Our resultant's going to look something like this. Obviously, this is not to scale. So, again, using the Pythagorean theorem, C is going to end up being the square root of 385 squared plus 27 squared. And we're going to round because I like rounding. And say that C ends up being 386 kilometers per hour. Then we do the inverse tangent. It's going to be of B over A, so 27 over 385, 4 degrees. And then lastly, we use the cardinal directions. It's going to be short of long, west is short, so west of south. So the resultant vector written out together is 386 kilometers per hour, 4 degrees west of south. Notice that in this problem, where the two numbers were closer together in size, 50 and 35, you ended up with a pretty big angle, whereas these numbers were much further apart in size, and you ended up with an answer that was the angle was a small number. All right, moving on. These down here are actually easier than the ones above. Calculate average velocity, instantaneous velocity, and acceleration in a given frame of reference. The great thing is that the county gives you all these formulas. So even if you don't remember anything about average velocity, if you pull out the handy-dandy county formula sheet, I did post one of these online, and you look under motion, you will see that there are two equations for V-average, which, believe it or not, is V-average. So we're going to use one of those. We're going to use V-average equals d over t. This is the simplest formula for velocity that there is. So we're going to have 175 over 12.8, and you end up with an answer that is 13.67 meters per second. Very difficult. The next one is the same way. It asks for acceleration. If you look on the formula sheet, there is a very simple formula right at the beginning for acceleration. A equals V final minus V initial over T. So the V final is 21, V initial is 8, and 7.4 is T. So we do 21 minus 8 over 7.4, which ends up being 13 divided by 7.4. And we get that the acceleration is 1.76 meters per second squared. All right, that's the end of the first page. There's the cover of my binder. If you've never seen it, it's so beautiful. Okay, again, I'm going to go through these that just require like writing pretty fast. We talked about these velocity time graphs during the bell ringers. So position versus time, there are three main ones. I'm going to put D versus T. The county does sometimes put P for position instead of D for displacement. I don't know why. So here are the three displacement graphs. This is no motion. The object is not, its displacement isn't changing with time, it is going nowhere. This one is constant velocity or uniform motion. And then this one is accelerated motion. There are only really two velocity versus time ones that you have to worry about. I didn't leave myself a lot of room. This is constant velocity again. So these two graphs actually go together. And then you have one like this. This is accelerated motion. So these two go together. And in both of these graphs, the slope of this line is the acceleration. So this one, the slope is 0, so it's a constant. This one, the slope is some number, so it's accelerated. Okay. Again, I'm going to just really briefly explain this next one. So free fall acceleration is independent of mass. Basically what this is saying is that when you're not talking about air resistance, everything falls at the same speed. In a vacuum, the mass of an object does not affect how fast it falls. It will always fall. So let's see, without air resistance, that's not how you spell resistance. The struggle is real, guys. Without air resistance, all objects fall at the same speed because their acceleration is due to gravity. Is all g equals 9.8 meters per second squared. Let's say you didn't remember that and you were asked, like, does mass affect acceleration in free fall? Well, let's look back at our handy dandy formula sheet. When we're dealing with velocity and acceleration in these units, mass is not anywhere in here. We didn't start having to include mass until we moved to forces. So, free fall acceleration does not depend on mass. Okay, now we have a taco diagram, which is actually a vector chart showing a thrown object. I'm just going to kind of go through some of the key facts that you might be asked about on the test. Vy, which is the vertical velocity, starts at its max value and decreases as the object travels upward. At the very top, it's 0. It is not traveling in the vertical direction at that moment. Then it increases again. Technically, it increases as a negative number over here because it has changed directions. Not super important for our purposes. So that's the story with Vy. Vy's, it's slowing down over here and it's speeding up over here are both due to the acceleration due to gravity. Let's write that. Increase and decrease due to g. Vx, on the other hand, is a constant throughout. It does not depend on g. Which means that Vx and Vy are independent of each other. It doesn't matter how hard you throw something in the horizontal direction, that's not going to change how it works in the vertical direction. All right, now down here at 11b, we are starting to look at Newton's laws. Newton's first law is the law of inertia. Like I said, Miss Morrison goes through a much more in-depth description of the law of inertia. I'm going to give my super ghetto definition, which is things want to keep doing what they're doing. If it's in motion, it wants to stay in motion. If it's at rest, it wants to stay at rest. An example of this is if you are in the car and your mom brakes really abruptly and you go kind of flying forward, that's because you wanted to keep moving. You had inertia. Turning over. Explain and identify examples of Newton's second law. So Newton's second law is, you guys can't see that, is the law of acceleration. The description of which is just F net equals ma. Force equals mass times acceleration. Examples of this are the fact that given the same amount of force, okay, let me rephrase that. Say you want to accelerate a motorcycle and a truck at the same acceleration. Because the truck has a much larger mass, it's going to take a much larger force to accelerate it. 11.2c, you may notice that there's not anything on here about Newton's third law. That means that the county did not tell us there was going to be a question about Newton's third law on the exam. Newton's third law is action-reaction, but we don't have to worry about that, apparently. So, apply F net equals 0 as the condition for constant velocity. What this is saying is, I'm totally drawing a blank. I'm going to awkwardly get myself together. Do, 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 do. Okay. Basically, F net being the condition for constant velocity, this comes from basically first law and the second law. If all your forces cancel out, then you're going to have no net force. So that means your velocity is going to be zero. But you can also think of it in terms of F net equals ma. If F net is zero, mass isn't zero, so acceleration must be zero. That is the crappiest equation ever. I'm sort of ashamed I wrote that. Okay, let's look at an example, and I think it's going to make more sense than me just rambling. A care package weighing 225 newtons reaches terminal velocity as it falls to the ground. What is the force of air resistance on the package? Now, terminal velocity means constant velocity. That's kind of important. So at constant velocity, we know that F net is zero, which means all the forces must be balancing out. If we were to draw a free body diagram, it would look something like this. There's only two forces acting on the object. The force due to gravity, which we call weight, is pulling downward. And the force due to air resistance is pulling upward. So they gave us the weight of the object. It's 225. So that means that F air resistance must also be 225 newtons. So no actual math required there. You do just have to make a couple of connections. Alright, so now it wants us to draw some lovely free body diagrams of a box on a horizontal surface and on an incline. This one should be easy. We drew so many like this. You have some object. Usually you have four forces. The forces that are definitely there are weight pulling down and the normal force, which comes from the surface itself, pulling up. Then for the problem to be pretty interesting, we also need an applied force and a frictional force. So again, that's normal, applied, weight, friction. If you're on an incline, things look a little bit different. So let's say we have our incline. I wish I'd thought to bring two different colored pens in here, but that's okay. The normal force is always, always, always perpendicular to the surface, which means that it sticks up at a funny angle in this problem. However, gravity always, always, always pulls straight downward. So gravity still looks like that. You actually end up dividing this into two separate vectors. We call this one F parallel and this one F perpendicular. That's not the perpendicular sign. F perpendicular. I seriously doubt you're going to be asked anything about this, but I've been wrong before. Alright, let's move on. So, identify, measure, and calculate centripetal force. A centripetal force is any force that moves something in a circle. There is a centripetal force holding the moon in orbit around the Earth, and there's a centripetal force holding the Earth in orbit around the moon. Again, even if you don't remember anything about centripetal forces, what you should do is come over here to your formula sheet and be like, okay, oh look, circular motion, F sub c, I bet that's centripetal force. Man, I'm going to use these equations. It's not very hard. So here they give us a mass of 1800, a velocity of 22, and a radius of 46. And we are looking for F sub c. One of those formulas that I just kind of briefly pointed at looked like this. Centripetal force is mass times velocity squared over radius. So 1800 times 22 squared, all divided by 46. You throw all that at your calculator, you're going to get the centripetal force is 18,939 newtons. Yay! I like the ones that actually involve math. I'm way less awkward at math than I am at just words. Now, what is the centripetal acceleration of a 77 kilogram runner who travels at 1.1 meters around a curve of 36 meters? Or travels at 1.1 meters per second around a curve. What is the centripetal force? So we know that mass is 77, V is 1.1, R is 36. A sub C is just V squared over R. So we're going to do 1.1 squared over 36, which gives us a centripetal force of 0.034 meters per second squared. To solve, see, they ask us for two things in this one. To solve for centripetal force, you can either just reuse the equation from the last one, or there's actually a third equation on the formula sheet that just looks like this. So that's a little bit simpler. We can just do 77 times our 0.034, and we get 2.62 newtons. All right. Explain gravity is a force dependent on mass and the distance between two objects. My whole explanation here, again, I'm getting tired of listening to myself talk, so really, if you want a better description of this, go read Miss Morrison's. But it comes from the fact that the force due to gravity looks like this. The formula does. It's on the formula sheet, as usual. G is a constant that you're given the masses of the two objects that are in question over the distance squared. So looking at the equation, it's pretty obvious that the force is going to depend on the mass. It's going to get larger the larger the masses are, and it's going to depend on distance, but it's going to get smaller the larger the distances are. Mass has a direct relationship with force. Distance has an inverse relationship with force. Okie dokie. All right, 14a, work and power. Calculate the work and power acting on a body by constant force. So a 43 Newton force is used to push a lab cart down a hallway that is 64 meters long. How much work is done on the cart? If the cart is pushed at 82, if the cart was pushed in 82 seconds, how much power was demonstrated? So we've been given a force of 43, a distance of 64, and a time of 82. Now again, you just have to find the equation that you think you're supposed to be using. You're like, oh man. I took the formula sheet that someone drew a beautiful picture on. I don't really know why that happened. But work, power, and machines, we have these two lovely formulas up here. They tell us that, get out of here formula sheet. They tell us that work equals force times distance, and power equals work over time. So for the first part, we'll do 43 times 64, which will give us 2,752 joules of work. And then we'll take that number over here, and we'll do 2,752 divided by 82. And we will find that P, power, equals 33.56 watts. Watts. You can tell I'm losing my mind a little bit. All right, let's look at the next one. This one's a little bit trickier, only slightly. It says an elevator lifts a total mass of 1,240 kilograms, a distance of 38 meters in 6.5 seconds. How much power does the elevator demonstrate? The thing you have to notice is that they have not given you a force here. They've given you a mass. We have a mass of 1240, a distance of 38, and a time of 6.5. Now, there's not an equation for work that includes mass. You have to be able to make the connection. Wow, I just noticed that Miss Morrison's key is actually wrong. We're special snowflakes discovering this together. She plugged this mass into the formula, but you can't do that. I just threw my pen. I'm so done with this video, you guys. I'm not even going to bother editing this because I hate listening to my own voice, so you're just going to have to deal with all the awkward pauses. Okay, so you have to make the connection that the force here is going to be the weight of the object, which is mg. So the first thing we have to do is we have to do 1240 times 9.8. And since Miss Morrison's key is actually wrong, I'm going to have to awkwardly pull up a calculator. Times 9.8. Thanks, Google, for being my calculator. So 12,152 newtons. From there, we can just use the same formulas for up here. We can say that the work is FD 12152 times 38. These numbers are going to get ridiculously large. So now I'm getting 46 or 461,776 joules. Then power will be that giant number divided by 6.5. So for my final answer, I am getting 71,042.5 watts. Again, this is, if you're looking at the key, this is actually a whole order of magnitude off from what Miss Morrison got, because she forgot to multiply by gravity. Shame. All right, let's talk about 5A, and then I'm actually going to save this very last one for part 2. I'm going to do all the momentum problems together. Okay, so identify different forms of energy to determine the transformation of energy from one form to another. We did a bell ringer like this that kind of walked you through different energy transformations. Here are some energy transformations you could have. KE, which stands for kinetic energy, to PE, which is potential energy. You could have the reverse of that. But then you can also have things like electrical energy to thermal energy. Thermal energy being like heat and light. You could have mechanical energy to electrical energy. You can have chemical energy to electrical energy. Basically, you just need to know, I don't know, an example of each of these and how they're possible. Kinetic energy to potential energy. I wish I had done that one the other way around, although this is certainly possible. But the easier example is to go the other way. PE to KE. If you jump off something, then that's going to be PE to KE. Electrical to thermal. This is a light bulb. It takes electrical energy and turns it into heat and light. Mechanical to electrical. This is what a generator does, whether it's a hand crank generator like the ones we played with in lab, or if it's a water wheel or something that's turning mechanical into electrical. Chemical to electrical is going to be batteries. There is some sort of chemical reaction that's creating electrical energy. All right, well, this has lasted 35 minutes, which was probably a waste of 35 minutes of your life. Hopefully, this helped with any questions you were having.